Hello, everybody, and welcome to our 6-week webinar, The Magic of Pretest, Post-Test, and Longitudinal Data Analysis. I'm William Bannon, bringing you the presentation from Stats Whisperer. Okay, very quickly, we realize that when people sign up for the 6-week webinar, they have come with goals. So if there's anything we can do to help you reach your goals, big or small, please let us know how we can benefit your learning. Okay, our objectives, okay? The objectives, as per the title as well, are 1, to review pretest, post-test data analysis, and 2, review longitudinal data analysis. In other words, we are going to celebrate the magic of these two great statistical methods. And by the way, you may be wondering about the title, what's so magic about pretest, post-test, and longitudinal data analysis? Well, that question will be answered as we go through this program. Now, we want to add on to our objectives. Our primary goal is not just to review information, but to illustrate how to apply the materials to produce original research, right? So we're focusing on practical and usable. In other words, we just don't want to learn information, learn facts, right? We want to be able to do, to accomplish, to produce original research. As Van Gogh has said, knowing is not enough, we must apply, and willing is not enough, we must do. So that's going to be one of our mantras as we go through this program. So our webinar agenda, right? So 6 weeks. First week, this week, right now, introduction. Right? Then next week, week 2, we're going to actually review and implement pretest, post-test analysis. In week 3, we are going to implement longitudinal data analysis. Then we're going to tackle, in week 4, attrition and missing data, which is a huge issue in these types of analysis. As well, in week 5, we're going to look at special considerations in pretest, post-test, and longitudinal data analysis, right? The latest cutting-edge considerations that exist for these methods, right? And then week 6, the write-up and report. How do we take our findings and put them into a report and publish them? Right? So that will be week 6. As we said, week 1 right now is the introduction. So perhaps the smartest thing we could do right now is define what we mean by pretest, post-test, and longitudinal data analysis. First, let's start off with our pretest, post-test study, okay? So there's many variants, right? So you can't really break it down just to 3. There's many variants, but for our purposes of statistical analysis, we're mainly concerned with these 3 traits. First of all, 1, the study has to have a dependent variable, also called an outcome variable, with 2 measurement points, right? 2 time points. For example, pretest and post-test. Second, number 2, most often there's an intervention or a stimulus between time points. And 3, the number of groups, right? So there's 1 or more groups involved in the pretest, post-test analysis, such as a control or an experimental. So if we're going to illustrate our definition of this study, right, this is what it would look like, right? So if we had a pretest and post-test study with an experimental and control group, right, and we graph the findings, this is what we would expect to see. So on the bottom axis, the x-axis, we see pretest is to the left and post-test is to the right. And on the y-axis, going straight up, we see happiness scores. So the happiness scores go from 1 to 5, 5 meaning the highest level of happiness, right? And the blue line represents the experimental group, and the dashed red line represents the control group. So the first point we look at is a pretest. You'll notice the mean scores for happiness for the experimental and control group are very similar, right? So the control is 3.0, the experimental is 3.1, right? So generally what that's indicating is this looks like the same group of people, which is what we want, right? They're very alike at pretest. Then after the interventions delivered at post-test, right? So the interventions delivered to whom? The experimental group, right? But not the control group. And that's why you see for the control group, the red dashed line stays flat, right? So at post-test, their mean score is about the same as it was at pretest. Why? Because there was no stimulus introduced, right? So we'd expect no change from pretest to post-test for the control. However, for the experimental, we see an upward slope denoting an increase in happiness scores. It goes from 3.1 to a mean of 4.1 for the experimental, right? So basically what we're saying is the experimental group had an increase in level of happiness, while the control group had the same level at pretest and post-test. So that's our classic pre-post study. Now we want to reference two terms, right? So first, the within group changes, right? So there we're looking, is the change significant within a single group? For example, the experimental group from pretest to post-test, the mean went from 3.1 to 4.1, right? So is that a significant change in happiness within that group? The other term we want to look at is the between group changes, right? So that's where we're comparing, did the change for the experimental group, was it significantly higher relative to the change for the control group? Now that looks like an easy answer, right? It looks like an easy answer for this study, right? Because the control group itself didn't have an increase from pretest to post-test while the experimental did. So of course we would say the experimental had a significantly higher change because the control group had no change. But, right, what if, you see the little yellow box there, what if this value, which is the post-test score, right, is the post-test score for the control group? So what if the control group post-test score was 3.5? Now that raises an alarm, right? Because now we have, instead of comparing 3.1 to 4.1 for the experimental to 3 and 3 for the control, now we're comparing 3.1 to 4.1 for the experimental, and now an increase for the control from 3.0 at pre to 3.5 at post. As I said, a slight alarm, right? So now it's starting to look more similar. Then we have to wonder, are the changes between the two groups significantly different, right? So we're going to examine that. Now next, of course, we define the pre-post, we must define the longitudinal study, right? Now, the big difference here is point 1, right? Or the first point, we should say, right? So it's a study with a dependent variable, also called an outcome variable, but the measurement points, right, are at more than 2 time points, right? So it's not just pre-test, post-test. For example, it might be pre-test, post-test follow-up, and there might be follow-ups to that follow-up, right? So that's what we mean when we reference longitudinal, right? And again, too, most often there's an intervention, and most often it's between the pre-test and post-test, right, unless it's an elaborate study. And again, number 3, there's one or more groups involved in the analysis over time. So if we give an example, it looks just like our pre to post study, except after pre-test and post-test, right? T3, which means time 3, is a follow-up, where the happiness score is measured again after post-test. Perhaps classically it's often 6 months later, right? So 6 months after post-test, we have the follow-up to see how the experimental and control groups have progressed after the pre-test, post-test. So what would that look like? Right? So if we were to graph that again, this looks just like our pre-test, post-test, except there's one more time period, right? So you see the x-axis at the bottom now has pre-test, post-test, and follow-up. Now the pre-test, post-test are the same. For example, the experimental still goes from 3.1 to 4.1 from pre-test to post-test. The control group still goes from 3.0 to 3.0 from pre-test to post-test. However, now we see for the experimental group, right, their mean of happiness from post-test of 4.1 decreases a little bit to 3.8 at follow-up. Now this is again a classic pattern in intervention research, right, because it's a dose response, right? So they just had their intervention, and at post-test they were really happy, right? And then, a few months later, the effects of the intervention start to wear off, that initial happiness might start to fade away, and it declines a little bit from 4.1 to 3.8, right? And then for the control, again, because there's no stimulus, there's a nominal difference of 3.0 to 2.9. So just about the same for the control from pre-test, post-test to follow-up. Right? Now, here's our big question, right? How do we test these changes between time points using statistics to identify which changes are statistically significant, right? That's what we're going to be doing with our SPSS software, right? So this will be illustrated in the presentations using SPSS software, right? For example, the pre-test to post-test change for the experimental group was 3.1 to 4.1. Is that significant? Is it not significant, right? We're going to be able to identify that and come out with some palpable answers. Okay, this is an iceberg, okay? What's an iceberg doing in a presentation about statistical analysis? Well, consider this. 99% of an iceberg is underwater and unseen, right, as portrayed in the image. So the graph analysis and findings we just presented, right, the pre-test, post-test findings, and the second longitudinal pre-test, post-test follow-up, that's like the 1% of the iceberg that you actually see, right? That's what everybody sees when you publish your findings, when you go to conferences and so on, right? They see that 1%. What they don't see is the 99% of the work that's behind the scenes to produce that graph and those findings, right? So that's what we're going to be looking at, right? We're going to look at data examination, data preparation, and other necessary analysis to produce that 1% that will be seen by the world. So what am I doing here? I'm just preparing us to say there's a lot behind producing those findings, and we're going to do that. Okay, now, Aristotle, right, stated for the things we have to learn before we can do them, we learn by doing them. Okay, so if we travel upon that thought, right, what will we need for this program? A sample study, right? So we're going to learn the analysis by doing the analysis via 2 sample studies, right? So specifically, we're going to test an intervention to increase happiness. The first one will be a pre-test, post-test study, and to increase happiness. The second will be a longitudinal study, pre-test, post-test, and follow-up. And all studies will have 2 groups, the experimental and control group. Now, of course, these studies are to act as templates, so when you have your own study to do, you could just follow along with how we did these studies. So if we're going to encapsulate what we're going to do with these studies, we're going to prepare the data, we're going to analyze the data, both in the context of pre, post, and longitudinal data analysis. Then we're going to write up our findings. There's our iceberg. Okay, so the basics of quantitative analysis. Now, in any game, you need to know the rules to play the game successfully. For example, if you were around in the 80s, this screen looks familiar. It's called Pac-Man. Right? So there was just a few basic rules you had to know to be successful at Pac-Man. Right? The little yellow guy who's Pac-Man eats the pellets. Right? Stays away from the ghosts. Eats the fruit. Right? If you swallow a big pellet, you could actually chase down a ghost. Right? So these are just rules of the game. Now, how does this relate to data analysis, right? There's some core concepts, right, for data analysis that we need to know to be successful at data analysis. If you would, it's just rules of the game for data analysis, and once we know them, we could be successful at performing a quantitative study over time. So these are 7 must-know core concepts, right? So if you've taken our programs before, this might be a bit of a review, although there is new material in there in the context of analysis over time. But these are the 7 core concepts we're going to need for this program to successfully implement quantitative data analysis. So first, let's actually go through them in live time. Now, first, there are 7 steps of quantitative data analysis. Right? Now we're going to go through each step one at a time to produce our studies. Now, Einstein said, education is not the learning of facts, but the training of the mind to think, right? So here you go. So these 7 steps aren't just facts. It's a way of training the mind or conceptualizing data analysis, right? Now, the 7 steps is a way to train the mind to think about quantitative analysis, right? Bears repeating. So here we go. Here are the 7 steps of data analysis. So first, we have our study map where we actually write out the relationships being studied. 2, data entry, right, where you enter the data from the hard copies into the statistical software like SPSS. 3, check data integrity to see are the data appropriate for analysis. Now, I'm just going over it in a cursory fashion here. We're going to actually go over it and implement it in depth. So this is just a little getting familiar introduction, right? And then 4, univariate analysis, where you look at one variable at a time, the characteristics of each variable, right? What's the average age and so on. Then 5, bivariate analysis, where we look at the relationship of 2 variables. And then 6, multivariate analysis, where we look at the joint effect of multiple variables on one outcome, right? And then 7, the write-up and report, which can be in tables and text. And so we're going to focus on 1 and 3 through 7, right? So data entry is a little beyond the scope of this presentation, but everything else we'll be covering in the context of data analysis over time. All right, 2. Parametric and non-parametric statistics, right? So parametric statistics are tests that make assumptions about the data being analyzed, such as a normal distribution and so on. So these include t-tests, correlations, regression, ANOVAs, things like that. Now, what if the data don't meet those assumptions? What can you do, right? So one thing you could do is use non-parametric statistics to address that fact, right? So these are tests that examine, typically through rank, relationships between variables that don't have as many assumptions, right? And interestingly, pre-post and longitudinal data analysis also have non-parametric equivalents. So this could be of great use, right, if we have data that don't meet the assumptions of parametric statistics. All right, number 3, descriptive and inferential statistics. All right, so descriptive statistics, such as our univariate statistics, are procedures used to describe the characteristics of the sampler population, right? So that's where we're just describing, like I said, you have age, what's the average age of the study participant, right? We're just describing the characteristics of the variables and therefore the characteristics of the sample and population. And then inferential statistics, those are our procedures that we use to test the relationship between variables, right? And we call it inferential because we make inferences, right? If A is related to B in our sample, we expect A to be related to B in the study population, right? We're making an inference from our sample findings about the study population, right? No trouble. Okay, the level of variable measurement, right? Now this is important. Why? Because a lot of the statistical tests that we're going to use, right, how do we know the right one? A lot of that depends on the level of variable measurement, right? So there are 4 levels in general, right? Here they are. Let's go through them. Nominal, categorical variable that can't be ranked, right? Such as gender, right? You have categories, male, female, 2 categories, and you can't rank them. As that is to say, you can't say one is better, or higher ranked than the other. Now 2, an ordinal variable is a variable that is categorical and it can be ranked, right? So it's poor, fair, good, excellent, right? So they're categories and you could rank them on top of one another, right? Now, one of the things about an ordinal variable is there's no equal space between measurement points, right? So if we were going to look at weight, 10 pounds between 0 and 10 and 10 pounds between 10 and 20 pounds, there's a finite amount between each, right? It's the same 10 pounds, but there's not the same distance between poor and fair necessarily as there is between fair and good. It's largely conceptual. And then if we have a categorical variable, be it nominal or ordinal, and it just has 2 categories, we often refer to that as dichotomous. Right? So this is the lingo that we'll be putting into use in this presentation. And then the other variables, right? Interval measures a variable along a continuum, right? Such as an IQ test, right? So you get 100 on the IQ test, you get 120, 130. Higher scores indicate a higher IQ, right? But there's no absolute 0, right? So if you get a 0 on an IQ test, it doesn't mean a complete lack of intelligence, right? So there's no meaningful true 0. So a ratio variable is just like an interval, except it has a true 0. So we're measuring along a continuum, but the 0 does mean a complete lack of what's being measured. For example, weight, right? So if you weigh something and has 0 pounds, that's a complete lack of weight, right? But as it goes from 0 to 10 to 20 to 30, it's a higher amount of pounds. Now, in real-world application, we often refer to variables as categorical or continuous. So they're categorical if they're nominal or ordinal, and they're referred to as continuous if they're interval or ratio. and we'll use that language in this presentation. All right, so the basics here. Core concept 5, the independent variable, right? The variable of interest that, right? The variable of interest we're trying to explain is the dependent variable. The independent variable is the variable of interest that explains the dependent variable, right? So that's the basic. Now, one important point in the context of our analysis is this, okay? The dependent variable, what we're trying to explain, is not the pretest score, nor is it, in the instance of pretest and post-test analysis, it's not the pretest score, and it's not the post-test score, right? Neither of those is the dependent variable you see on the top here. See, the lower boxes, right? If you minus, see where it says the pre is being minus from the post. So if you have a 3 at pre, happiness score of 3 at pre, and a happiness score of 4 at post, right? That's a change of what? +1. Right? So if you minus the pre from the post, it's a change of +1. So whoever got that score had an increase of happiness in the +1. That's the difference between the pre and post. That's the dependent variable. What we're trying to explain is the difference, the change in between these time points, right? So we're not concerned with pretest or post-test scores so much. We're concerned with the change from pretest to post-test. That's the dependent variable we're looking at. Right now, covariate variable, what's it called, predictor or control variable, right? So the variable in the data set, it's not the focus of our study, but we have to include it in analysis because it has a significant impact on the dependent or independent variables, right? So what does that mean? Okay, here we go. So suppose in our analysis we find this, right? Suppose our dependent variable is the change in happiness scores from pretest to post-test, right? Then we look at our study group as a predictor, and we see that there's a significant relationship between study group and change in happiness scores, right? That's what we saw in our graph, right? In other words, the experimental group had a significantly higher change in happiness scores, okay? And then we have our, we'll go over this in a moment, p less than 0.05. It's a significant relationship. So we're happy about that, right? It looks like our study group had a significantly higher change in pretest to post-test scores. But what if we introduce the covariate gender, right, into this model? It's quite possible that the significant relationship between study group, right, and change might just disappear. Right? So that's why covariates are so important. We want to be able to say that study group predicted change in the happiness scores, over and above the covariates such as gender, right? So it could be if you put gender in there and it's no longer significant, that could indicate that, there's a bias in gender, like perhaps the intervention worked better for gender, right? Rather than study group, right? So we want to examine all that. So that's why covariates are so important. All right, we're getting toward the end here of our core concepts. So number 6, there are 3 dimensions to every relationship. So if we look at the relationship between variable A and B, there are always going to be 3 dimensions of that relationship that we must pay attention to. 1, significance, 2, directionality, and 3, magnitude. So let's review those right now. So significance, also called statistical significance, refers to the probability, also known as p-values, that reflects how likely the relationship is a result of chance. Okay? So the relationship between the variables can be statistically significant, which is denoted by p, which is the p-value, typically less than 0.05, or not statistically significant, where p is greater than 0.05. Now, 0.05 is just a statistical standard, right? Sometimes 0.01 is used, sometimes 0.001 is used, but as a standard, 0.05 is often used, and we'll use that. So what does by chance mean? So by chance means it appears that there's a significant relationship, but in reality, there is not. Right? So 0.05 reflects that we're willing to accept that 5 times out of 100, findings appear significant, right? But they're not. They're just by chance. Okay, so this could be addressed through our PPP, which stands for our pizza probability presentation, right? This will tell us what chance actually means. Okay, so for example, a man is in an office and he's asked to hold a slice of pizza by a client signing forms. A coworker approaches him and assumes he likes pizza because he's holding the slice, right? And then the man says, I actually don't like pizza. You just happened to see me holding this slice by chance, right? So we even use that in our regular vernacular, right? So the relationship appeared significant, but in reality, there was only the appearance of significance. Right, so in statistics, if we conduct 100 tests, we accept that 5 will also give us the appearance of significance, right? But will just be by chance, right? In other words, 5% of the time, we'll get sort of faked out, like the man holding that slice of pizza, where the findings are presented as significant by our software instead of an actual slice of pizza. Right, so statistical significance is reflected as probability being less than 0.05, p less than 0.05, or p greater than 0.05, where it would indicate not statistically significant. Then 2, the second characteristic of a relationship, directionality. It's either positive or negative. Right? So a positive relationship between two variables means as one increases, the second also increases, right? So that would mean, for example, in our study, right, we have a pre to post change in happiness. That's our outcome. That would mean as pre and post scores increase, income level also increases, right? That's a positive relationship. Now, a negative relationship means as one score goes up, the other goes down, right? So as one score increases, the second score decreases. Now, in that example, that would mean as pre to post change in happiness scores increase, right, the level of income for participants decreases. So there'd be a relationship, right, where as people have lower and lower income levels, right, they're having a higher and higher pre to post test change. Now in statistics, the negative relationship is often indicated by a minus sign in front of the statistical coefficient, right? So a positive relationship does not have a minus sign in front of the coefficient, right? And we'll illustrate this in our analysis, of course. Right? So for example, a Pearson's R correlation coefficient, right, is an R. So if R equals negative 0.35, right? There's a minus. That means there's a negative relationship between variables. If r equals 0.35 and there's no minus, there's a positive relationship between variables, right? And that'll be more meaningful when we actually do the test. Right? So there we go. Minus sign, negative relationship, no minus sign, positive relationship. Now, 3, the magnitude. Now, the magnitude is very important, but it's often neglected in statistical analysis, believe it or not. So magnitude reflects the strength of the relationship between the variables, right? So how impactful is one variable upon another. Right? So the magnitude can be expressed in a few different ways, but one of the most common ways are the effect size. So let's discuss that here. Okay, so a key in statistical analysis, right? So a relationship between two variables might be statistically significant, but the effect size might be so small that the relationship is almost inconsequential, right? So thus, the effect size is a huge consideration, right? Because not all significant relationships are equal, right? And let's illustrate that. So if we consider as our outcome variable, our dependent variable, the pretest to post-test changes in happiness score, we might say there were some other factors happening, right, that had an impact on the level of change of happiness between pretest and post-test, such as emotional well-being, right? Generally, how happy are they feeling at that moment in time? The weather, is it good or bad? Does a dark sky inspire a dark mood, right? Good or bad hair day, right? So how do you feel about how do you look? How's that affecting your happiness development, right? Now let's suppose that all 3 of these factors have a significant impact on pre to post changes in happiness scores. So they're all statistically significant. That's our assumption. Rather, our assertion. Okay, so here we go. So we have our little study map here. So you'll see on the left, the first box says weather, right? Good or bad, that's the least important, right? So we find that has the least important impact. It's significant, but it only has a small effect on the pretest to post-test change. The hair day, right? It's moderately important, and so that has a medium effect on the pretest to post-test change. But on the bottom left, we see emotional well-being. That's the most important, right? You can see that, right? So if you're developing your happiness and you come in feeling good, right, that could have an impact on your pretest to post-test happiness change, right? So they're all significant, but the magnitude, right, the effect size between the predictors and the outcome are different. So we need to consider that. Thus, right, the indicator of magnitude we'll look at are the small effect size, medium effect size, and large effect size. And we'll discuss how to identify those when we're ready. And if you'd like an acronym, right, so you could say the human relationships are kind of like these statistical relationships, right? So in a human relationship, you have to savor daily miracles, right? So SDM. So S significance, D directionality, and M magnitude. And lastly, haste or paste, right? So save the syntax. So you'll notice when using SPSS, when you set up a statistical test, you could either click OK and it runs the test, or you could click paste and you can actually save the syntax for that test, right? So if you save the syntax, you can see if you did the test right. You can rerun the test later on. If you like, you have a paper trail of what you did. So saving the syntax is always encouraged, right? So, paste or haste, we say you could click OK, but that might be a bit hasty, right? You don't have your paper trail. Can't repeat the procedures. So we would recommend paste over haste. Okay, so now we've reviewed the rules of the game, the rules of engagement, right? What we need to know to engage in this data analysis so we can approach the steps of quantitative analysis. So keep in mind, step one is the study map. Right? So we'll now structure the study map based upon the study goals. All right, here we go. So again, here are the 7 steps of data analysis, and we're examining step 1, the study map. So apply it to our sample study. So step 1, the study map. So this is the stage of analysis where the study variables and hypothesized variable relationships are presented in both text and diagram. Now this is going to provide a lot of clarity and organization. So we're going to specify exactly what we are looking at, right? And that's what we should be able to do at the start of any study, right? So if we're foggy at this point, the trajectory of the entire study might be off, right? So as Einstein said, if you can't explain it simply, you don't understand it well enough, right? So here we go. We're going to explain our study as simply as possible so we understand it as well as possible. So research question 1A. So that will be our pre-test, post-test analysis. Okay, so is the happiness intervention associated with significantly higher happiness scores for pre-test to post-test? There you go. And our hypothesis is participants assigned to the happiness intervention will evidence significantly higher pre-test to post-test happiness scores while those in the control will not, right? So that sounds familiar because that was our graphed expectation, right, early on. Now the dependent variable, again, it's not pre or post-test scores, it's the pre and post change in happiness scores. Our independent variables are study group, the experimental control, and we will consider 2 covariates, education and income levels. And picture's worth 1,000 words, so here you go. Here we have those relationships in a diagram, picture form. Right on the left, we have our predictors. Then on the right, we have our dependent variable, the pre-test to post-test change in happiness scores. Now, if you could graph the relationships like this, you understand the study implicitly, I would say. And then our second study is our longitudinal study. Remember, pre-test, post-test follow-up. So just a slight alteration in these study maps, right? So is the happiness intervention associated with significantly higher happiness scores from pre-test to post-test to follow-up, right? So a little longer graph there, okay? And then the hypothesis is, of course, participants assigned to the happiness intervention will evidence significantly higher pre-post follow-up scores while those in the control will not. Right? And again, the dependent variable is going to be changes between pre-test, post-test to follow-up, right? Changes in happiness between those 3 time points, right? The independent variable, experimental and control group, and the covariate variables, education and income, right? So all very clear, all mapped out. Here we go. And there's our diagram. As you can see on the left, we have our covariate variables 1 and 2, an independent variable. And on the right, the dependent variable changes in happiness from pre-test to post-test to follow-up. All right, now here's a little contact theory for you here, right? So we just want to mention these two things now. So as we refer to them throughout the program, it sounds familiar, okay? So we have options for doing different statistical tests when the study is pretest, posttest, or longitudinal, right? So if we have a pretest, posttest study, yes, we could do the repeated measures GLM, which we'll look at, but we can also use different scores, right? Now, when it's longitudinal, the next line, we're just going to use repeated measure GLM, general linear models. So you don't have to understand this at this point. Just the next time you hear it, it's just going to sound familiar. We can say, oh, I remember that from a short time ago. Okay, now, we want to address a little of step 3 in this presentation because the checks of data integrity are formidable. So let's take care of a little this week, and then we'll do the rest as we go. So the checks of data integrity. So there are 4 areas where data integrity must be checked. First, there's statistical power. 2, there's missing data. 3, there's test assumptions. And 4, study instruments. Now we're going to be, like I said, going through these at different times. We're going to address statistical power today in this presentation. 2, missing data, that's going to be the subject of week 4. As we said earlier, that's a big topic in longitudinal data analysis. 3, test assumptions and study instruments we'll address for the pretest, posttest, and longitudinal analysis, respectively, in weeks 2 and 3. So don't worry, we're going to be doing all these tests. Okay, so a power analysis, what are we talking about here, right? So the power analysis is most often used to indicate the needed sample size for a study to indicate if we have sufficient statistical power to answer the research questions / hypothesis. On a practical level, if I told you I was doing a study and you asked me how many participants I had and I said 4, you would say that doesn't sound like enough. So I would say, how about 4,000? You might say, well, that sounds like too many, right? So the question becomes, what number in between 4 and 4,000 do we need for our research study, right? So the power analysis will tell us. So the power analysis can be conceived as a dish of 4 ingredients. 1, there's statistical power, and these need to be set in our power analysis. Now, statistical power as a convention must be 0.80 or above, so we'll set ours at 0.80. So 1 is statistical power. 2 is level of probability, or alpha as it's called. So as we said, that's often set at 0.05. So for our power analysis, it will be. And then 3, the effect size, right? So what effect size do we want to observe between the variables of interest, right? The independent, dependent variable per se, right? So when there's no reason to select a big or small effect size, the default is to select a medium effect size, which we will be doing in our power analysis, right? And then 4 is a sample size. Now, how do these relate? So if you set 1, 2, and 3, power, probability, and effect size, the power analysis will reveal number 4, the sample size needed for our study to have sufficient statistical power. Right? So you need a software, right? A software to perform the power analysis. Here, we will use G-Power, right? Because it's a statistical software online, right? It's appropriate, it's effective, and it's available free online at this address, right? So there's many other software programs for a power analysis, so should feel free to look around. But we'll use G-power here. Right? So, as we said, we want it to look familiar, right? For pre-test, post-test, we can use different scores, right? And if we use different scores, right, the statistical test used in that pre-post analysis, right, the final multivariate analysis, will be the multiple linear regression model, right? So, if that's the case, we'll do a power analysis based on a multiple linear regression model, right? And that would be the power analysis appropriate for that pre-test, post-test study. Okay, so if you open G-Power, you will see this dialog box, right? So just make the settings as so, right? So in the upper left where it says test family, we select F-test, then right to the right under statistical tests, linear multiple regression, right? Fixed model R squared deviation from 0. And the type of power analysis, a priori, right? Compute required sample size given A alpha, power, and effect size, right? No trouble. So then in the input parameters below to the left, you'll see the effect size set at 0.15, which is medium. A error prob, that's alpha, 0.05. And power, right, in the parentheses, 1 error prob minus error prob is 0.80. Right, so that's our settings for effect size, right, for probability, and for power, right? And also in a regression model, you have to specify the number of predictors, right? So let's say we have 4 predictors, right? So we're only considering 3 variables, but, you know, just in case we want to include an extra variable, we'll just set it at 4. Now, when it's all set up like this, in the lower right, you click Calculate, and the numbers are filled in. Now, second from the bottom, you'll see total sample size, and you'll see there's an 85. So that's telling us we need 85 study participants, right, for our study to have sufficient statistical power based on those settings, right? So that's pretty straightforward. Right, so longitudinal, right, data analysis. So here we're going to be looking at the repeated measures general linear model, right, as our tool for multivariate analysis. It's also called a repeated measures ANOVA and MANOVA, which can be very confusing. So that's why I'm mentioning it, right? So you might hear it called that too. Right, so we'll do our power analysis now in G-Power on this procedure. Right, so you'll see to the right next to F-test what's changed, right? So now our statistical test is an ANOVA repeated measures we've selected within factors, right? And then you have the same type of power analysis, the a priori, and the input parameters are a little different. So now the effect size, F in parentheses U, a medium is 0.25. Then we have the same settings for power and probability. Then it says number of groups 2. Remember, that's our experimental and control. And the number of measurements is 3, which reflects our pre-test, post-test follow-up. All right, now, you don't click calculate yet, right? Next, you click in the lower left options. And under options, this dialog box will come up, and you must click as in SPSS because we're using SPSS, right? Then we click OK. Then we go back, right, to our original dialog box, then click calculate, and there we go. So the total sample size needed is 80, right? Now this does not have the covariates built in there, but it's saying we need a sample size of 80 for our pre-post follow-up analysis. Okay, so next week we're going to look at for pre and post. We're going to look at the rest of checks of data integrity minus the missing data. You know, that's the week 4. and then univariate, bivariate, and multivariate analysis. And so it's going to be a full week. All right, thank you for watching.